Right, so here's our, again, stoichiometry with mixtures, and then this is our stoichiometry map with mixtures here. And so let's take a look at the problem involving this here. Number 77. A phosphate rock quarry yields rock. Rock is a mixture of different minerals. Rock that is 79.4% calcium phosphate. So this rock is not pure calcium phosphate. This rock contains just 79.4% calcium phosphate and 20.6% other stuff. The raw material used in preparing calcium dihydrogen phosphate, a fertilizer known as superphosphate. The rock is made to react with sulfuric acid according to the equation. So the calcium phosphate in the rock reacts, the other stuff doesn't react, and it produces this. What is the smallest possible mass of rock in kilograms that must be processed to yield 0.500 tons of fertilizer? And so 0.500 tons of fertilizer, half a ton of fertilizer, that's going to be this, the calcium dihydrogen phosphate. And so what we do is we go from tons of fertilizer to grams of fertilizer. From grams of fertilizer, actually fertilizer is this, so we'll go from tons of calcium dihydrogen phosphate to grams of calcium dihydrogen phosphate. From grams of calcium dihydrogen phosphate to moles of calcium dihydrogen phosphate. For moles of calcium dihydrogen phosphate, we'll go to moles of pure calcium phosphate. From moles of pure calcium phosphate, we'll go to grams of pure calcium phosphate, and then we'll go to grams of rock. But the rock is not pure calcium phosphate. The rock is 79.4%. So this is just like this problem here. You know, we'll get the oxygen, but we want air, which is a mixture. And so we'll have to figure out how many grams of air. Well, this is the same thing. How many grams of rock? Well, we'll get the grams of calcium phosphate, but the rock is not pure calcium phosphate. It's 79.4%. And so we'll have to add one more step to that. And so let's see what they did here in their answer. Well, actually, they went from tons to pounds, 2,000 pounds in a ton, and then pounds to grams. And the grams, they went to kilograms. So I wouldn't do kilograms and kilomoles. I just do grams to moles. So they do this kilomole type stuff. And so let me set this up the way I set it up here. So it'd be similar to this problem here. So calcium phosphate, Ca3PO4, 2 plus sulfuric acid, we need 2 H2SO4s. This is going to yield calcium dihydrogen phosphate, CaH2PO4. H2PO4 is a 1 minus, so we'll need 2 of those. And then calcium sulfate, we get 2 calcium sulfate here. And so we're starting off with 0.500 tons of calcium dihydrogen phosphate. And then we'll go from tons to pounds using, you know, there are 2,000 pounds in a ton. And then pounds to grams. And then grams to moles. And so we'll get moles of calcium dihydrogen phosphate. From moles of calcium dihydrogen phosphate, we'll go to moles of calcium phosphate over here. And then from moles of calcium phosphate, we'll go to grams of calcium phosphate. Okay, and so these are just standard stoichiometry. Now, the trick step here is that the calcium phosphate is part of a mixture which we call rock. And the rock is going to be, well, we want to know how many grams of rock do we need. Well, this is what we have. For every 100 grams of rock, there is going to be 79.4 grams of calcium phosphate. 79.4 grams of calcium phosphate. And so here, this will allow us to cancel out the calcium phosphate and get rock. We'll need more rock because the rock's not pure calcium phosphate. Does that make sense? And so this would be the additional step that we do on top because we're dealing with mixture. All the regular stoichiometry, we'd stop here, with pure. But this is an additional step that's required for mixture. Look at number 78. Carborundum, silicon carbide, SiC, is widely used as an abrasive in industrial grinding wheels. It is prepared by the reaction of sand. This is silicon dioxide, or silicon 4-oxide, with the carbon and coke. So we take some silicon dioxide, quartz, plus 3 carbons, yields silicon carbide plus 2 carbon monoxide. What mass in kilograms of carborundum can be prepared from 727 grams of coke? That is 88.9% carbon. Well, coke is a mixture. And so let me set up number 70. This is number 77. Let's set up number 78. Why don't you set it up like this? So I'll write the equation up here. First, we're dealing with a mixture called coke. Coke contains 88.9% carbon. 88.9% carbon. That means this. I have 88.9 grams of pure carbon for every 100 grams of coke. And so here, the way I'd set this up is SiO2 plus 3 carbons yields SiC plus 2 COs. Now I don't have pure carbon. They give us 727 kilograms of coke. So I start off with 727 kilograms of coke, which is a mixture of carbon. And so I'm going to go from kilograms of coke to what? I'd probably go from kilograms of coke to grams of coke. And then from grams of coke to grams of pure carbon. So go from, because for every 100 grams of coke I have 80.9 grams of carbon. And so from grams of carbon I can go to moles of carbon, and then from moles of carbon I can go to moles of silicon carbide or carborundum, and from moles of silicon carbide they want kilograms. And so I'd go from moles to grams and then grams to kilograms. That would be it. So this is another mixture problem. Let's look at number 79. See if we could look with this. A sludge containing silver chloride is a waste product from making mirrors. The silver may be recovered by dissolving the silver chloride in sodium cyanide solution and then reducing the silver with zinc. The overall reaction is this. This is a combination of Lewis acid base and redox here. And so this is a waste product, silver chloride. What they want to do is they want to recover the silver metal. And so they can do this chemistry here to recover the silver metal itself. What minimum amount of sodium cyanide is needed to dissolve all the silver chloride in 40.1 kilograms of sludge? That is 23.1% by mass silver chloride. So we have something called sludge here. And so they tell us what the sludge, the composition of the sludge is. The sludge is 23.1% silver chloride. And so what that means is I have 23.1 grams of pure silver chloride for every 100 grams of sludge. So they give us 40.1 kilograms of sludge. So what would I do? I'd go from 40.1 kilograms of sludge to grams of sludge. And then from grams of sludge, I would go to grams of, yeah. So I'd go from grams of sludge to grams of silver chloride using this conversion factor here. And then once I have grams of silver chloride, I would go to moles of silver chloride. And then from moles of silver chloride, I'd go to moles of sodium cyanide. And then from moles of sodium cyanide, I would go to grams of sodium cyanide to kilograms of sodium cyanide. So that would be the amount of sodium cyanide that's required to do it. So they use the kilomole, kilogram thing, which I'm not really into, but let's see what they do here. I like to get a consistent units. I don't like this kilomole, kilogram stuff. I like to keep things the same as much as possible, even if it requires doing extra steps. The chemical reaction that describes what happens in an automobile battery is this. This is interesting. What's the PbO2 called? Lead-4 oxide. Pb is lead metal. The interesting thing is lead-4 oxide is the oxidizer, lead is the producer. And so lead-4 oxidizer, lead metal producer. What fraction of lead in PbSO4 comes from PbO2? Well, it looks like 50% of it, because we end up with two leads here. So one of the leads comes from PbO2, the other comes from Pb. So it looks like 50% by mole comes 50%. So also by mass. If the process uses 29.7 grams of PbSO4, what mass in grams of PbO2 must have been consumed? Well, this one we don't really need A. We just go from grams of PbSO4 to moles of PbSO4, and then from moles of PbSO4 to moles of PbO2. So this is just a standard stoichiometry, and the moles of PbO2 to grams of PbO2. So A is irrelevant, answering part B. It's just a straightforward stoichiometry from part B. 81. Hydrogen and chlorine are produced simultaneously in commercial quantities by the electrolysis of salt water. This is a redox reaction. Yield from the process is 61% by mass. What mass of solution, that is 9.6% sodium chloride, must be processed to obtain 105 kilograms of chlorine? And so this now we have multiple percentages. So now they're trying to confuse you. They're trying to confuse you because now we got two percentages, and then people who don't write any units are not going to, are probably going to blow this problem, because you have to write out the units of this. The percentages are two different things. And so this would be an advanced problem. But before we do this advanced problem, let me do one more standard problem. And so here we got two percentages. And the two percentages is really going to screw some people up. I don't want to do that yet, because I want to do one more problem before that. The one problem I want to do before that is this one, number 75. The laboratory test of 12.8 grams of aluminum ore. Aluminum ore is not pure aluminum. Aluminum ore is a mixture. And so, aluminum ore is a mixture of aluminum and other stuff. If the aluminum compound in the ore is aluminum oxide and it is converted to the pure metal by the reaction, what is the percentage of aluminum oxide in the ore? Okay. So they want, what is the percentage of aluminum oxide in the ore? So in this ore, they want to know what is the percent aluminum oxide. In other words, how many grams of aluminum oxide per 100 grams of ore? You know, times 100%. That's basically what they want. Or, we don't have to have it per 100 grams of ore. If we want to figure out the percentage by mass, this is what we do. Or, we do percent aluminum oxide by mass is equal to the grams of aluminum oxide over, in this case, grams of ore times 100%. Now, in this problem, they give us the grams of ore. And so what we want is the grams of aluminum oxide per 12.8 grams of ore times 100%. And so what we need to do is we need to find out how many grams of aluminum oxide there are. And so in the previous problems, we're given this percentage composition. In this problem, we have to figure out what is the percent composition using some stoichiometry. Well, the way we're going to do this using stoichiometry is this. They tell us the ore yielded 1.68 grams of aluminum. And so we would do it like this. 2Al2O3 solid plus 3 carbon solids yields 4 aluminum solids plus 3 CO2 gas. This is a redox reaction. And so what we have is we have 1.68 grams of aluminum. And then from grams of aluminum, we could go to moles of aluminum. And then from moles of aluminum, we could figure out how many moles of aluminum oxide that must have come from. So we'll get moles of aluminum oxide. And then from moles of aluminum oxide, we'll get grams of aluminum oxide. And this grams of aluminum oxide is what we need to plug in here to figure it out. So let's see how they did it here. Let's take a quick. So they went from grams of aluminum to moles of aluminum. So we did grams of aluminum to moles of aluminum, molar mass is here. And then from moles of aluminum to moles of aluminum oxide. So it's a 2-to-4 ratio. The mole ratio is here. And then from moles of aluminum oxide to grams of aluminum oxide, this is the molar mass. And so they end up with 3.17 grams of aluminum oxide. We plug that in here. For every 12.8 grams of ore, we had 3.17 grams of aluminum oxide. So what is the percentage? We'll just take the ratio divided times it by 100%. We get 24.8%. So we only had 3.17 grams of aluminum oxide and 12.8 grams of ore. Do you see that? So this problem is a little different. The other two problems, we're using the percentage. This problem, we have to figure out what the percentage is. Number 75 is a very common problem. We're always interested in the composition. Like, what is the percent oxygen? What is the percent carbon dioxide in air? Do something like this. Okay, now let's go to this one, which is a bit tricky. Why don't you try number 81?